What does science currently know about dark matter and dark energy? One of the most intriguing questions in modern cosmology is what are the nature and origin of dark matter and dark energy? They make up more than 95% of the matter-energy composition of the universe, but they are invisible to normal matter and light. Scientists have been trying to understand their nature and origin for decades, using various observations and experiments. In this essay, we will explore some of the current theories and experiments that aim to shed light on this dark mystery. Dark matter is a hypothetical form of matter that does not interact with electromagnetic radiation, but exerts a gravitational influence on other forms of matter. It was first proposed by Swiss astronomer Fritz Zwicky in 1933, who noticed that the galaxies in the Coma cluster were moving faster than expected, implying that there was some unseen mass holding them together. Later, other astronomers found more evidence for dark matter, such as the rotation curves of spiral galaxies, the gravitational lensing of distant objects by foreground masses, and the cosmic microwave background radiation. Dark matter is estimated to make up about 27% of the total mass energy of the universe, but its exact nature and composition are still unknown. Scientists have proposed a number of different theories about what dark matter might be made of. One leading hypothesis is that dark matter consists of exotic particles that are beyond the standard model of particle physics, such as weakly interacting massive particles, WIMPs, axions, or sterile neutrinos. Before we discuss these candidates in more detail, let us first explain why we need dark matter in the first place. The evidence for dark matter comes from various observations that indicate that there is more mass in the universe than what we can see with our eyes or telescopes. For example, the rotation curves of spiral galaxies show that stars at the outer edges move faster than expected from the visible mass distribution. This implies that there is an invisible halo of extra mass around each galaxy that holds it together by gravity. Another example is the gravitational lensing effect, which occurs when light from distant sources is bent by the gravity of massive objects in the foreground. By measuring the amount and shape of this distortion, we can infer how much mass is present in the lensing object. In many cases, this mass is much larger than what we can account for by normal matter. One possible explanation for this missing mass is that it is made up of weakly interacting massive particles, WIMPs. WIMPs would interact with ordinary matter only through gravity and the weak nuclear force. This would make them very difficult to detect, but there are a number of experiments underway that are searching for WIMPs. These experiments use detectors that are placed deep underground or in space to shield them from background noise. They look for rare events where a WIMP collides with a nucleus or an electron in the detector and produces a small amount of energy or light. Some of the most sensitive experiments so far are Xenon 1T, LUX Zeppelin, and Dama/Libra. Another possibility is that dark matter is made up of axions. Axions are hypothetical particles that were proposed to solve a problem in particle physics. They would be very light and would interact with ordinary matter only through gravity and the strong nuclear force. Axions are also very difficult to detect, but there are a number of experiments underway that are searching for them. These experiments use devices that convert axions into photons, light particles, in the presence of a strong magnetic field. Some of the most promising experiments so far are ADMX, CULTASC, and CAST. Finally, there is the sterile neutrinos theory. These particles could be produced in high-energy collisions at particle accelerators, such as the Large Hadron Collider, LHC, at CERN, or detected by sensitive detectors underground or in space. Sterile neutrinos would interact with ordinary matter only through gravity and possibly through mixing with other types of neutrinos. They would have a very small mass and could travel at speeds close to the speed of light. Some of the experiments that are looking for sterile neutrinos are Mini-BUNE, IceCube, and Cotrin. Gravitational waves are ripples in the fabric of spacetime that are produced by massive objects accelerating. They were first predicted by Albert Einstein in his theory of general relativity. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves from the collision of two black holes. This was the first direct detection of gravitational waves, and it provided a major confirmation of Einstein's theory of general relativity. However, gravitational waves are not only a way to test Einstein's theory, but also a tool to dark matter. For example, if a black hole is surrounded by a cloud of gas, the gravity of the black hole can pull the gas in, forming a disk of orbiting matter. This disk of matter can then be a source of dark matter. While dark matter attracts and holds galaxies together, dark energy repels and causes the expansion of our universe to accelerate. Dark energy is estimated to make up about 68% of the total mass energy of the universe, but its origin and nature are even more mysterious than dark matter. One way to understand dark energy is to think of it as a property of space itself. According to Einstein's theory of general relativity, space can have energy and pressure even when it is empty. This energy and pressure can have a positive or negative value, depending on how space behaves under stretching or shrinking. If space has a positive energy and pressure, it acts like a repulsive force that pushes everything apart. This is what we call dark energy. Another way to understand dark energy is to think of it as a fluid that fills space. This fluid would have a negative pressure that counteracts gravity and causes the expansion of space to accelerate. This fluid could be related to a hypothetical field called quintessence, which varies in space and time and has different equations of state. A third way to understand dark energy is to think of it as a manifestation of a modified theory of gravity. Perhaps Einstein's theory of general relativity is not the final word on how gravity works, and there are some corrections or extensions that become important on large scales. These corrections or extensions could mimic the effects of dark energy and explain the accelerated expansion of the universe. One of the main challenges in studying dark energy is to measure how it changes over time and space. To do this, we need to observe the history and geometry of the universe using various methods and probes. Some of the most important methods and probes are supernovae. These are exploding stars that can be used as standard candles to measure distances in the universe. By comparing the apparent brightness and redshift of supernovae, we can infer how fast the universe is expanding at different times. The first evidence for dark energy came from supernova observations in 1998, which showed that the expansion of the universe is accelerating. Cosmic microwave background, CMB. This is the relic radiation from the early universe that fills the whole sky. By analyzing the tiny fluctuations in the temperature and polarization of the CMB, we can learn about the initial conditions, composition, and evolution of the universe. The CMB also provides a way to measure the geometry and curvature of space. Baryon acoustic oscillations, BAO. These are sound waves that traveled through the primordial plasma in the early universe and left imprints on the distribution of matter. By measuring the characteristic scale of these imprints, we can determine how space has expanded over time. Large-scale structure, LSS. This is the pattern of galaxies and clusters of galaxies that form due to gravity and dark matter. By studying how this pattern changes with distance and redshift, we can probe how dark energy affects the growth of structures in the universe. Gravitational lensing. This is the bending of light by gravity that can magnify or distort the images of distant sources. By measuring how much lensing occurs on different scales, we can map the distribution of matter and dark energy in the universe. Dark matter and dark energy are two of the most fascinating and mysterious aspects of our universe. They challenge our understanding of physics and cosmology, and they offer us a glimpse into the unknown. By using a combination of theoretical models and observational data, we hope to unravel their secrets and learn more about our cosmic origins and destiny. They also have implications for other phenomena in the universe, such as the formation and evolution of galaxies, stars, planets, and life. Scientists are continuing to study dark matter and dark energy, and they are making progress in understanding these mysterious substances. However, there is still much that we do not know, and it is likely that we will gain a deeper understanding of the nature of reality and our place in it in the years to come.